Hey there and welcome. Today we're going to talk about one of the most powerful tools you'll find in Precalculus, the Finite Geometric Series. You know those sequences of numbers where each one is just a multiple of the last? Ever wonder how to add them all up super fast? Well, we're about to show you the formula that makes it a piece of cake. And you'll see how it pops up everywhere, from Wall Street to Silicon Valley. All right, let's get into it.
So, here's what we've got on tap. We're going to kick things off with a little summing challenge. Then I'll hand you the slick formula that solves it. After that, we'll take it for a spin with a few examples. I'll point out some common traps to watch out for, and then, this is the cool part, we'll see how this exact same math can help map out your financial future.
All right, so first things first, let's frame the problem. We're dealing with something called a geometric sequence. That's just a fancy way of saying you start with a number and you just keep multiplying it by the same number over and over. Now, adding them up one by one, it can be a total pain, and that's exactly the challenge we're going to solve today. Okay, so take a look at this series. 3 plus 6 plus 12 plus 24 plus 48. Now, sure, you could just pull out your calculator and add them up, no problem. But what if this thing kept going for, say, 50 terms, or even 1,000? You're not going to do that by hand, right? There's got to be a better way, and trust me, there is. And that better way is, you guessed it, a formula. It's this beautiful, elegant tool that's built for exactly this job. It lets you add up any finite geometric series, I don't care how long it is, in just one single clean step. Ready to see it? And here it is, the star of the show. The sum, which we call S sub n, is just a1, that's your first term, times, get this, 1 minus r to the nth power, all of that divided by 1 minus r. It looks a little intense at first, I know. But look closer. Each piece has a really simple job. A1 is just where you start. R is that number you keep multiplying by, the common ratio. And n, that's just how many things you're adding up. That's literally it. And you know, this formula didn't just fall out of the sky. It actually comes from a really clever little algebraic trick. It's not magic at all. It's just pure mathematical elegance. Let me show you how it's done.
You've got to see this. It's so clever. First, you just write out the sum normally. Then you write it out again right below, but this time you multiply the whole thing by r. Now, here's the magic move. You subtract that second equation from the first, and when you do that, poof, almost everything in the middle just cancels out. It's awesome. You're left with just the very first term and the very last one. A little quick algebra to factor things out, and boom, you've got the formula. It just goes to show how one smart trick can solve a huge problem.
Okay, enough with the theory. The only way to really get a feel for a new tool is to actually use it, right? So let's do that. We're going to walk through 3 examples, starting simple and then leveling up. Let's put this formula to work.
So we're back where we started, but this time we are armed and dangerous. We have our formula. And the first step, every single time, is to figure out what your variables are. All right, let's break it down. Our first term, a1, is staring right at us. It's 3. For the common ratio r, just pick any term and divide it by the one before it. So 6 divided by 3 gives us 2. And we can just count them up. There are 5 terms, so n is 5. See? Piece of cake. Now for the fun part. We just plug those numbers right into the formula. The sum is 3 times, let's see, 2 to the 5th power minus 1 all over 2 minus 1. That simplifies really nicely to 3 times 31, which is 93. And there you have it. So much faster than adding, right?
Okay, let's try another one. This time, notice the numbers are getting smaller. We sometimes call this a decaying series, but guess what? The formula doesn't care. The process is exactly the same. We need the sum of the first 6 terms. Okay, our first term, a1, is 100. To get our ratio r, we take 50 and divide it by 100. That gives us 1/2, or 0.5. And the problem flat out tells us we want the first 6 terms, so n is 6. And the cool thing here is that our formula works perfectly fine when r is a fraction less than 1. So we plug everything in. We've got 100 times the quantity 1 minus 0.5 to the 6th power, all divided by 1 minus 0.5. Yeah, it looks a little messy with the decimals, but that's what calculators are for. And the final sum comes out to exactly 196.875. Done.
All right, time to level up. You're going to see this big Greek letter, sigma, all over the place in Precalculus and beyond. It's called sigma notation, and it's just a really compact, kind of nerdy way of writing down a long sum. Don't let it scare you. It's actually giving us all the clues we need.
Okay, let's decode this. To get our first term, a1, we just plug in that starting k value, which is 0. So that's 5 times 3 to the power of 0, which is just 5. The number with the exponent on it, the 3, that's our common ratio, r. Easy enough. But now, here's the part where everyone gets tripped up, so listen close. How many terms are there? It says from k equals 0 to 7. So you might think, oh, 7 terms. But wait, you have to count the 0. So it's 0, 1, 2, 3, 4, 5, 6, and 7. That's 8 terms. N is 8. Super important detail.
Now that we've got our variables, we're back on familiar ground. We plug them in. It's 5 times the quantity 3 to the 8th power minus 1, all of that divided by 2. This simplifies down to 5 times 3,280, which gives us our final answer of 16,400. And just like that, you've cracked sigma notation for geometric series. Not so bad, was it?
So now that you're an expert at using the formula, let's take a second to talk about how not to use it. There are a couple of really common mistakes people make, and if we can get ahead of them now, you'll be golden.
Okay, these are the two big ones, so you'll want to remember these. First up, that counting error we just talked about. It's so easy to do. If a sum goes from k is equal to 0 to 7, that's 8 terms. Always, always, always double check your n. And second, what if r is 1? I mean, think about it. If r is 1, our formula has you dividing by 1 minus 1, which is 0. The universe would explode. Well, not really, but your calculator will give you an error. The fix is super simple, though. If you're just multiplying by 1 over and over, you're just adding the first term to itself again and again. So the sum is just n times a1. That's it. So you might be thinking, this is cool for math class, but am I ever going to use this in real life? And the answer is a big, resounding yes. It shows up anytime you have compounding growth. And you know, there's no better example of that than money. Think about this very real-world scenario. Let's say you invest $1,000 every single year for 10 years straight. And that money is sitting in an account that earns 8% interest each year. How much do you have at the end? Well, figuring that out involves adding up the future value of all those separate investments. And that, my friends, is a geometric series problem.
So let's translate this into math. The A1 is our annual investment, $1,000. The number of terms, n, is 10 for 10 years. Now what's r? Well, if you're earning 8% interest, your money is being multiplied by 1.08 every year. That's our growth rate, and that's our r.
So you take those values, pop them into our trusty formula, and run the numbers. And here's what you get. After 10 years of putting in $1,000 a year, that's 10 grand total out of your pocket, your account would actually be worth almost $14,500. That extra 4.5 grand, that's the magic of compounding interest. And we were able to calculate it precisely with this formula. See, this isn't just a bunch of abstract math for a test. It's a real tool for figuring out how things grow in the real world.
And that pretty much wraps it up. This formula is like a key that can unlock any system where you have compounding growth or decay. We looked at finance today, but this same math applies to biology, technology, even the way ideas spread on the internet. So, the question I'll leave you with is this. Now that you have this key, what other patterns in your world do you think it could unlock? Thanks for watching.